see your questions. So Christian, if there's any questions, just tell me.
Okay, we'll do.
Or you could just talk.
Okay. Yeah. If anybody wants to raise their hand or whatever, I can let Emmanuel know. Okay. All right. Well, welcome to another MCRN Colloquium. So today we're lucky to have Dr. Emmanuel Fleurantin, who I've known for, I guess, at least 5 years now after the first summer school in 2020, doing some COVID rapid response research at the time. And it's been great working with him ever since. Just to introduce him a little bit, right now he's a postdoctoral fellow at George Mason University. Before that, he was at the University of North Carolina for a little bit. He's been working with Chris Jones throughout this time as a postdoc. He got his PhD in 2021 from Florida Atlantic University, working with Dr. Jason Morales-James. Today, he's going to be talking to us on the spectrum of Schrödinger operators interacting at two distinct scales. So very much looking forward to it. Anytime we hear Schrödinger, it's always exciting. So with that, please take it away.
Okay, all right. Thank you very much, Christian, for this wonderful introduction. So I'm thankful for being invited to give this talk. So I want to thank my collaborators, Jeremy and Chris, that are collaborators on this work. Okay, so then let's get started. So multiscale systems, they're everywhere, right? So basically, you're looking at this box here. So this is like atmospheric jet stream, where you have like the scale here is like thousands of kilometers. So it's a large organized flow. It guides motion, etc. So then there's smaller scales that's embedded in that, which are turbulent eddies, which are in meters. Another large scale phenomena that you could see here would be like deep blue open water. Okay, so deep blue open water, they are usually like in basin scale, so kilometers. And then what you see in there is like there's diffusion and mixing, and that are in centimeters. This is a very small scale that's happening in those basins. Also, what you have here is like you have this hurricane tropical cyclones, which are in hundreds of kilometers. And then what happens there is like you have a eye wall mesovortex that just kind of is the wall of the hurricane. This is in meters, right? So you have these two type of scales interacting with each other in general. Okay, so then the challenge here is like now I'm looking at multiple scales, right? So basically how they interact with each other, and I'm looking at the what happens, right? Different scenarios that could happen. So first thing, I could choose to ignore the small scale, but then I lose essential structure. Second thing is I could ignore the large scale, but then I miss the global organization. The next thing is I could treat them independently, right? But then interaction matters in most of these cases. Okay, so then my fundamental question will be, when two spatial scales interact, right, do their effects combine additively, or does the interaction create emergent behavior? This is on my overarching question. Okay, so then the goal of this talk is I'm going to present a model problem where I can answer this question rigorously, right? That's a general idea for this. Okay, so then this is the talk that I'm going to present. I'm talking about Schrödinger, spectrum of Schrödinger operators. So what is a Schrödinger operator? In this particular case, Schrödinger operators, there are differential operators, and they have a certain form. So you could think about an operator as I linearize about a steady state. So this is the structure that it has, and this is Laplacian minus W, and this is something that acts on something called a function space, right? So it's essential for describing particle behavior and under potentials in scenarios like quantum mechanics. In this particular case, right, the spectrum of the Schrödinger operator is providing key insight into energy levels, right? And then I'm going to analyze these interactions, and then this will help me understand complex behaviors, right? So you could imagine I have potential, I add another potential at the different scales, and I'm looking at what comes out of that. right? So then research in this area supports advancement in quantum computing, material science, and also fundamental physics. All right. So then the next thing that I want to discuss is there's the approach that I'm going to use. So then there's two scale potential frameworks. So then I'm going to have one potential that's at the order 1 scale. I'm going to add another potential that's at order epsilon scale. So this is what W is made of. Is made of a near field potential and a far field scale potential, right? So then these potentials, they act on different distinct spatial scales, and that enables separate contributions. And of course, I'm going to do this with a tool that I'm very familiar with a dynamical systems approach. So you will see like building a stable, unstable manifold, center manifolds, and I hope to get some counting based on that, or just understand the behaviors by looking at this dynamical system approach. Okay, and then of course I'm going to just try and develop some spectral additivity principle. So then if I have the near field potential V0 and I add this far field scale potential, and I'm going to look at this, I'm going to perturb the far field potential, and I'm going to see what behaviors that I'm going to get with that. So then the idea here is if I perturb it for a sufficiently small parameter, I'm trying to understand the eigenvalue count. Hello?
Go ahead, Justin.
Sorry, I didn't mean to interrupt you, Emmanuel. Also, I don't know how this works. I don't know how to. I know raising my hand would cause it to interrupt and make a noise. I apologize. So my question was for your particular framework. What function space are you working in?
So this is L2R3, right? So I'm looking at L2 function spaces, but then I'm going to look at radial solution also. So then L2R3 will become L2rad. I mean, so
Yes, sir.
function spaces on radial solutions, which is a very good question. Thank you for that. Okay, so then beyond that, there's applications in quantum mechanics, reaction diffusion systems, stability analysis, and nonlinear wave equations, etc. Okay, so then what I'm going to do now is, of course, I'm studying Schrödinger operators. So then this potential W decomposing into two potential, the near field and the far field. And then the near field, the far field is increasingly delocalized as epsilon becomes very small, right? So we perturb it. So then the main result for this particular case is I'm going to look at the eigenvalue count. And my hope is to show you that it is, of course, additive across scales. Okay, and there's applications to this in quantum mechanics and reaction diffusion systems. Okay, and then there are some prior work that are known. For example, there's this single scale theory where Valentine Bargmann has classical results on the number of bound states, eigenvalues for central radial potentials. They provided upper and lower bounds in terms of integrals involving R vis of R. Okay, and there's also the famous work of Barry Simon, which look at weak coupling. So then Barry Simon analyzed like how bound states appear and disappear as coupling strengths varies, right? So eigenvalues in the weak coupling limit. So basically, he kind of showed that precise asymptotics for eigenvalues near threshold. There's the work on Kloss and Simon. So basically, they look at threshold resonances. So you have eigenvalues that pop up at the end of the essential spectrum, basically, or at the limit of the essential spectrum there. So then the idea here is it's well known that if these potentials, they're weakly coupled, the perturbation theory works well, right? So then what we aim to do in this case, we're going to look at least one non-perturbative potential, which is order 1 strength. And then we interact it with far field potential that's going to be at a different scale. And then we try to make some rigorous analysis of the spectral interaction. That's basically the idea. So then the key technique that I'm going to use is I'm not going to go into detail because this is a colloquium, so I'll just briefly say what they're about. So compactification, you could say it makes an unbounded problem tractable. So basically, imagine that you have the space going to infinity on both ends. So basically, it treats infinity as an accessible boundary, basically. Okay. And then I'm going to use blow up analysis. So blow up analysis would mean that I'm going to have a fixed point in my eigenvalue problem. And when I analyze a spectrum, it's going to have a double zero eigenvalue. So then the idea here is to blow up this fixed point, usually, and look at the dynamics on a circle or a sphere, and you get information on what's happening, on what's actually happening there. I'm going to use separation of scales, which I'll show you in the next steps. And then I'm going to look at a technique called bootstrapping. So basically, bootstrapping means like I'm going to assume that something is close, but I'm going to do some analysis that at the end is actually even closer. Okay, and then the idea here is I'm going to do some topological counting argument. So this winding number interpretation, basically, I'm going to look at by this winding number is going to give me information on the eigenvalue count that's being contributed by V0 and also that's being contributed by V1 epsilon. So then this is the problem here. The problem here is I have a Schrödinger operator, right, on L2, the L2 R3. So it's like the space X variable is 3D, right? So then, of course, like I said before several times, the potential decomposes into two scales, where I have the near field and the far field potential. And then so what I'm showing here is how I'm going to write this operator. So the Laplacian minus W is actually, I have to go I have to put this coordinate into spherical coordinates, so into r, theta, and phi. And what you see in the Rex box is what the Laplacian look like in spherical coordinates. But since I'm looking at only radial potentials, so basically, so then the angular variable goes to 0. So then all I'm left with is what you see at the bottom. So then the operator is exactly what you see on the right-hand side. And then since I'm looking at the spectrum of this operator, I'm going to set up something called an eigenvalue problem. So I'm going to take the operator times u is going to be equal to lambda u, and I hope to get some information on the operator. That's the basic idea of that. Okay, so then the main question that I'm going to ask is how do eigenvalues depend on scale separation for this particular case? And I hope that after this talk, I'm able to elucidate some information on how to answer this question in this particular setting. Okay, so then, so how do I go about doing the scale separation structure? So in the inner scale, so then this I have an order R, so a constant, so 5, 6, 7, 8. In the outer scale, I'm going to do a scaling. I'm going to take the independent variable, I'm going to multiply it by epsilon, where epsilon is very small. And the reason why I do that is because I want to separate the effect of V0, right, the near field potential, and the effect of the far field potential, right? And you'll see that more carefully later. And I'll show a picture later that you'll see how things work in a minute. So in the idea here is I'm going to look at a system when I separate the scales that dominated by V0, right? And I'm going to integrate it up to a threshold. And then in the far field, I'm going to look at a system that dominated by V1. I'm going to integrate it to a threshold R, which is epsilon to the alpha. And then you'll see later on as I go through the slides why we pick alpha to be this value is because once we get to the threshold, we could clearly see the effect of V0 and V1 independently. And you'll see that in the examples that we're going to show later. Okay, and then this is going to be a two-model problem connected via geometric analysis. Again, I'm not going to go into detail. This is going to be an overview. And of course, you'll say, I have to make some assumptions. And the assumptions that I'm going to make are basically, how does V0 and V1, how do they decay? Okay, so we need to have some assumptions for that. So in the idea here, I want smooth potentials. And this boundary that you see here is basically, I need to show that they decay at infinity and avoid certain resonances, right? And then these are just standard in spectral theory and not restricted for physical interpretation. So the key point here is that each potential has finitely many bound states. Okay, so then what this is saying, like, I want these two potentials to be smooth. Okay, I want them to decay sufficiently fast, at least faster than polynomial decay, a little bit. Okay, and then I want to make the final assumption that at the zero is not included in something called the point spectrum or the discrete spectrum. You could see that this is the where I'm actually counting the amount of eigenvalues that's in this operator. Okay, so then if once I have these assumptions, what this does for me is like I could ensure finite eigenvalue count and well-posedness of this of the dynamics. So then you'll see this theorem very briefly, and this is basically the result of what we're trying to show with the spectral additivity component, just trying to look at the different scales. So then what this is saying basically is like, so if I define this notation MV to be the number of positive eigenvalues of Laplacian minus V, so then what this is saying essentially here is I could count the contribution of what V1 brings exactly, right? So basically, for this particular problem, the essential spectrum is going to be from essential spectrum or continuous spectrum is from -infinity to about 0. Now, there's going to be a spectral gap. And by spectral gap, I mean, so I'm going to look at Laplacian minus V0. So the smallest eigenvalue that's contributed by V0 on the real axis, from this smallest eigenvalue to 0, right? So let's say 0, 1, for example, there is a gap. And the idea that we're trying to propose here is by adding this perturbed potential in the far field, you actually get eigenvalues that pops up, right, in this spectral gap. And this is only generated by adding this this perturbed potential in the mix. So this is what this notation is saying. So this mu naught, 0 mu naught, is what we call a spectral gap, where mu naught is the smallest eigenvalue that's generated by Laplacian minus V0, the effect of V0. And then what we're trying to show here is we're trying to show that basically what is the eigenvalue count of the operator Laplacian minus W is basically the eigenvalue count of Laplacian minus V0 plus the eigenvalue count of Laplacian minus V1. And we'll show that it separates very nicely in this particular case. So that's the general idea. So then again, I'm not going to go on the proof, and I'll show you a picture in a minute. So then the idea here is something that I'm very familiar with, right? So I could transform the eigenvalue problem to being a heteroclinic connection. I'm going to compactify the domain. So by making infinity 0 will be 0, but infinity will be 1 in this particular case by using this particular compactification parameter. And the idea here is I'm going to look at the winding about the complex plane. So basically, once I generate my ODE, right? So then I'm going to look at a total angle accumulation from where I shoot at 0, for example, to where I end at 1. And every time I have an eigenvalue, this total angle accumulation is going to be a multiples of pi for this particular problem. So the idea for this particular thing is, this is the dynamical system approach, is basically I'm going to look at this eigenvalue count by trajectories connecting unstable manifolds to center manifolds, which is something that I've been working on like mostly throughout my studies. Okay, so this is the proof strategy. The proof strategy here is the idea, and I'll show you in a minute how I do that. The idea here is I'm going to have two systems, right? So I'm going to have a system called the inner system, which you see on the left-hand side here. And then the inner system will have a fixed point theta, right? So then it'll have its own scaling, order 1, for example. And then I'm going to, because it's a compactified phase space, it has a fixed point, and this fixed point has certain stability. So I'm able to shoot in the compactified variable on this unstable manifold that you see here, which is VWU, right? So then I'm going to derive the outer system. The outer system is the size system that you see on the right, and I'm going to show you exactly how I do it in a second. But then the idea here is to, in between two non-eigenvalues, mu1 and mu2, right? what I need to show is once I shoot the unstable manifold here and the center manifold there, right? Once I shoot those on the threshold, which is yellow, the sigma k, what this gives me here is this gives me just in between two non-eigenvalues, I could get this heteroclinic connection, which is this red dot that goes from theta equals sigma equals 0 to sigma equal 1 essentially, right? So then the key term here is how we're going to control this unstable manifold that's in the inner system, and how we're going to control the center manifold that's in the outer system. So then we will set a radius delta, and then what we'll have is we'll have the V0 driven system, right, is going to lie in a tube delta of the true solution, right, which is the full system. Also, for the size system, we're going to set a tube, and then we'll say that the V1 driven system is going to lie on a tube of the true solution in the full size system. So the idea here is once I shoot to the threshold, I get the contributions given by the V0 system and the V1 system. And the idea here is to apply an intermediate value type argument on the distance in yellow that you see here in the threshold to say that in between there must exist a true connection that connect the unstable manifold to the center manifold at infinity. That's the general idea there. Okay, and the sigma k here is this is the points that are on this threshold. So the sigma k is the difference between the center manifold of psi 1 mu 1 and the center manifold of psi 1 mu 2, and then we're trying to get a 0 of this sigma k to get this red connection that you see here. Okay, that's the general idea of what we're trying to approach. And to be more specific, and again, I won't go into detail. So how does this scale separation works? So of course, when you're solving these problems, you have to set an eigenvalue problem. So you set the operator LP equals lambda p. And in this particular case, for the first scale that we're going to look at, the order R, the order 1, right? We set the eigenvalue problem and we solve it as usual. And of course, we're going to have boundary conditions. The boundary condition is that the derivative is 0 on sigma equals 0, and then we needed the wave function to decay all the way to 0 at infinity. That's the general idea for that. Okay, so this is the essential scaling here, and the essential scaling that you see is this R equals epsilon over rho over epsilon. The idea here is if I divide this LP system, I'm going to do a change of variable where the scale separation is going to be given by this R that you see here. So now this new system is going to be this LP where I'm going to have this epsilon squared terms that's going to appear. Now what's good for me is like once these epsilon squared terms appear, I'm able to divide this whole system by epsilon squared and thus diminishing the effect of V0, but just having the effect of V1, right? So then the V1 takes over, right? So then the idea here is, so then this new system that I'm going to try to get is the following system, where the eigenvalue problem now is V1 dominated, right? Because what I'm trying to do here is I basically scaled out the epsilon squared in the V1, and now I'm able to look at the behavior of the far field potential. What happens to this eigenvalue problem using the far field potential? So essentially what I'm able to do here is going to have the same boundary condition as the first one, but in this different scaled independent variable that I'm looking at. So now what I'm able to do is, if you look at the top box, if I turn off, if V1 is 0, I'm going to only get the effect of V0, or if epsilon is turned off. So basically, remember, V1 is epsilon squared V1. So as epsilon is 0, basically I'm going to get only the effect of V0 here. And then because of the boundary condition that I set that V0 decays at infinity, if I'm at infinity, the effect of V0 are negligible. So then I'm only getting the effect of V1 here, right? Using this eigenvalue problem. So notice that this mu here is going to be also, it has a relationship with lambda, and I'm going to present it later. So basically, by doing this transformation from the top box to the bottom box, I'm able to get two different set of eigenvalue problem where one potential dominates the behavior on one end, and the other far field potential dominates the other behavior on the other end. Okay, so once we get an eigenvalue problem like this, what do we do? What is our next step? So then my next step in this particular case is I'm going to convert this second order ODE that we have for both of this system into a first order system, right? So then what the idea here is once I get this first order system, I'm going to directly convert it into angular rotation. So this is what you see here. So then the top box is what's happened once I have this this eigenvalue problem that I transform into a first order ODE, right? And then now I'm going to use angular variable. So you could look at theta is arctan V over P. And if I differentiate that, I'm going to get theta equation that's completely independent of R, right? So then I get pure angular, pure winding count based on that. And the sigma dot here is the compactification parameter. Remember, sigma was R over R plus 1. So then this essentially, this inner system that's going to be V0 dominated is going to be essentially what's going to drive the right-hand side of my scale dynamics. And of course, the boundary conditions becomes fixed points, right? So at sigma equals 0, I'm going to have a regularity at the fixed point 0, 0. And at sigma equal 1, I'm going to have decay and infinity at this particular fixed point. All of these come from the boundary condition that we set. And of course, in the second eigenvalue problem that you saw, what happens here is you also have the psi system that's going to be V1 dominated, right? And it has a corresponding first order ODE that we compactify and that we also put in angular formula. Okay, so then what am I going to do next? The idea here is, so I have two model problems. So on one end, I have the compactified system in theta and sigma, right? So basically, the idea here is I'm going to keep only V0, and then I'm going to set lambda equal to 0. So if I do that, I'm going to get the eigenvalue count of, so basically setting lambda equal to 0 and evolving this ODE will give me the number of eigenvalue that's going to be above 0. So basically above lambda is equal to 0. So the amount of jumps on that will give me that. Okay. So then for this particular system, so then also setting lambda equal to 0 for this problem, and because this is V0 dominated, this is also going to give me the total eigenvalue count, the total amount of jumps that's generated by V0 on the real axis. So I'm trying to look for this mu0 that I showed you in the beginning, right? On the right-hand side, I'm going to do the same thing. So remember, this is the V1 dominated system. So this is the psi tau, right? And then so I'm going to pick two non-eigenvalue parameters. I'm going to shoot. This is going to go to a fixed point here, which is pi over 2. This is going to go to a fixed point here, which is negative pi over 2. But remember, so I'm just going to go up to this threshold. So the idea here is what you'll see later is technically, in principle, these things are different scales. So I cannot, so sigma epsilon here is not really equal to tau epsilon. So then you're going to see that I'm going to do a change of variables to get those two systems to be theta essentially. And then when I do the intermediate value theorem on this bar that you see in the middle is essentially going to apply for the theta system on both ends, right? But just the idea for now here is I'm going to take the theta sigma system, shoot using the unstable manifold, take the psi tau system, shoot using the center manifolds at non-eigenvalue parameters, and then just trying to get them to reach the threshold, and hopefully that I could have enough control on those manifolds as I do it. Okay, so then let's focus on the V1 dominated system. So for the V1 dominated system, so there's going to be key technical estimates. So, well, when I say V1 dominated system, I mean that I'm going to look at essentially the contribution that's being offered by V1. So then there's going to be 4 regions, right? So in the previous slide, see in the sigma system, there is a region here that is called from theta equals 0 to sigma star, right? And then I need to have control of this unstable manifold up to there. And there's this other region in something called a plateau from sigma star to sigma epsilon that I also need to have this control over, right? So this is what I'm going to try to control here. So then for the inner plateau, I'm able to get this estimate using stable manifold theorem, for example, right? For the outer plateau, I'm able to get these estimates using the bootstrapping arguments, right? So what I mean by that is for this red region that you see at the bottom here is, I see that the full solution of this full system with both V0 and V1, it stays order epsilon close to the V0 model, right? So then what this means here is like first I have to look at the epsilon equals 0 case separately. So then at the epsilon equals 0 case, I get a fixed point that has double zero eigenvalues. So we have to do some blow up analysis so we're trying to get control of epsilon as it goes to 0, even the epsilon equals 0 case, right? So then we are able to get estimate on the theta 0, our decays, even when epsilon equal to 0. So then the next step is to use the bootstrap argument, right, on this red region that you see there, this light red region. So we assume that we have a certain, we have an eta that's a difference between the full system and the V0 system. And then the idea here is we're able to use some Gronwall type argument to show that we also have this, this estimate that we had here that we thought eta was bounded by is actually smaller when we get to the end. So then we're able to get full control of this. We're able to have like full rigorous control of this unstable manifold up until the threshold that we care about. Okay, so then remember what I was saying about wanting them to be the same variable. It turns out that there is a way to go from the psi to the theta variable, right? We could do so by using what you see in this the box here. So you could say tan theta is equal to epsilon tan psi. So then you could relate the outer and inner angle. So then when you reach the threshold, you actually be in the theta parameter. So they'll be the same variables, right? So this is the argument that we see here at the top. So in this red region, we're able to use bootstrapping argument to get this corollary that you see at the top. So then I'm able to, the full solution is theta plus, and then the V1 dominated solution is theta 1. And I'm shooting from psi equals 1. I'm able to get full control using singular perturbation theory in the white region, and in the red region, just use a regular bootstrapping argument. This is the general idea for that. So then also what's also important in these type of problems is in this threshold, I want to, so remember this is sigma k. This is the, sigma k is points. It's like I'm looking at it's a difference function. Sigma k is the difference between this top blue curve that you see here and this bottom blue curve that you see here. The idea here is I need to have matching conditions at those thresholds, one coming from 0, the other one coming from infinity. And then the idea here is I need to show that I have monotonicity. So I only have crossing in one direction. So what I'm going to do here, the idea here is to actually look at the derivative of the sigma k respect to mu and show that it's always positive. So that ensure that I don't have my eigenvalues in this region when it cross, they are unique. That's the idea there. Okay, so then what is the result of when we combine everything together? So when we combine everything together, we're able to get this red curve that you see in the middle. So then we're able to rigorously show that we did the sigma system on its own, we did the psi system on its own, we matched them together, we get a intermediate value theorem connection in between. So we get this red curve that you see here that gives us the heteroclinic connection that we wanted to see in the beginning, that confirm a high eigenvalue count. Okay, that's a general idea for that. So then, okay, so then this previous slide kind of gives me the eigenvalue count that's generated by V1, right? So then all I'm doing here is I'm approximating the true solution for sigma, approximating the true solution for psi, connect them to a threshold to get this heteroclinic connection. And this heteroclinic connection, if it jumps by a multiple of pi, the amount it jumps by, and you'll see examples in a minute, is going to tell me coming from infinity the amount of eigenvalues that's generated by V1. So of course we have to also be careful. We have to look at the eigenvalues that are generated by V0, and to do this, we simply use Sturm-Liouville theory. So basically, the order 1 eigenvalues. So what happens here is we treat V1 now as a purely perturbative, as purely perturbative. And what we could do here is we could just kind of have full control. So all I need to control is this theta minus coming from 0 and have full control all the way until it gets to infinity, right? So then I have full control. We're able to establish that. And so once we have full control of this unstable manifold, what we're able to do here is we're able to get the order 1 eigenvalue count for this that's generated by V0. Okay, so then so this is the idea for that. So then we have some examples which hopefully I didn't go into too much detail, right? So the examples are how we do that. So when we look at Laplacian minus W, we actually have example that we look at. So we look at the first scenario, which we have 2 Gaussian potentials. And then we have a second scenario where we have a rational potential, but that decays with the condition that we want. And we have a Sesh potential. And we also have a third scenario where we have like it's like a Cauchy squared potential. It's like this quotient that we have for the potential, and this is like a rational, like you have these rational potential also. But they both decay in the same way that we want to, at least a little bit faster than polynomial. So what you'll see in a minute is like in all cases we confirm that the total eigenvalue count for W is at Laplacian minus W is actually a total eigenvalue count generated by V0 and the total eigenvalue count generated by V1. Okay, so then how we do that? So we treat them separately. So in the first case, when we looked at the eigenvalue of Laplacian minus V0, and then we just kind of looked at the V0 system, we get one jump, right? So then we get the unstable manifold starting from 0 in this theta system, jump by 1 multiple of pi. So this is telling me that Laplacian minus V0 has 1 real eigenvalue. Okay, so then I do the same thing for the psi tau system. So then with purely V1, right? And I get in some cases I get 2 jumps, in some cases I get 3 jumps. By jump I mean that I look at the theta difference between the end of angles where it gets to the end minus the beginning, right? But in all 3 cases consistently, we're able to get we're able to confirm that Laplacian minus V0 has 1 real eigenvalue, and then so we're able to also get the other V1 dominated system, Laplacian minus V1, to either have 2 eigenvalues in the spectral gap or 3 eigenvalues in the spectral gap. But then what you'll see here when I put the full systems together, Laplacian minus W, you'll see that this is a combination of both. So this is like a simulation of what it looks like. So you could see that I'm trying to find eigenvalues generated by V1 here. So I'm only varying the gamma for the tau system. So then so we have to say that gamma is going to be mu over epsilon squared. So then that's the general idea. So then so mu is epsilon squared gamma. So then what you see here is the eigenvalue parameter, the mu, that's on the sigma system on the left, and then the eigenvalue parameter gamma, that's in the tau system at a different scaling on the right. So the idea here is I have three different shifts of the unstable manifold on the left, corresponding to three different jumps for the center manifold on the right. Notice that the center manifold started somewhere like -5, and you can see as the eigenvalue parameter vary, right? As it's getting well, the closer it is to zero, the higher the jump, right? So the idea here is I want to use an intermediate value theorem type argument that connects the center manifold on the right to one of the stable manifolds on the left, on one of the unstable manifolds on the left. And the idea here is to use this intermediate value theorem type argument to show that there, in between two non-eigenvalues in the tau system, there actually exist connections that connect to these unstable manifolds in the sigma system that will correspond to jumps, and that will correspond to eigenvalue counts. And that's the basic idea. So then this is if I look at the full systems together, so what you see here in the left, for the sigma system, I'm looking at the sigma system with V1 and V0 combined. And as you could see, when the eigenvalue is very small, when I vary it, the highest jump that I get is 3. So remember that the V0 contributed 1 eigenvalue, and then V1 contributed 2. You see 3. And then in the full non-approximated tau system that has both V1 and V0, you also get 3 jumps. So you get both matches. So what happens now is that as I integrate to the threshold, right? So integrating to the threshold for the unstable manifold, I get exactly 1 jump for the sigma system. So I could capture that 1 jump, and I capture 2 jumps from the tau system. So then that gives me 1 plus 2, which is the total eigenvalue count for MW here is 3. Okay, I do the same thing for the scenario 2. So then you could see that when I combine the sigma system with both the V1 and V epsilon, I have 4 jumps. 1 generated by the V0 potential, and 3 generated by V1. And I also have 4 jumps in the tau system when I add both potentials together, looking at the effects. So then once I integrate, once I apply the thresholds, what you see here, you'll see that the V0 system, it basically gives me effect of V0, which is 1, so I don't go all the way down, and it gives me the effect of V1, which is 3. So then the total eigenvalue count for MW is 1 plus 3 is going to be 4. Okay, and I do the same for the third scenario. You see the black color is 3 jumps as the eigenvalue parameter goes to 0. And then I also get 3 jumps by looking at the full tau system. So if I integrate it to the threshold, what you'll see is 1 that's generated by V0 and 2 generated by V1. So then when you do the eigenvalue count for this one, you'll get 1 plus 2, which is 3. So then in the 3 test cases, I set epsilon to be 0.1. So in the case where I have, the first scenario, I get, like I said, MW is 3. Second scenario, I get 4. And then in the fourth scenario, I get MW is 3. And these are confirmed by using this argument that we have. We could also argue that there is a heteroclinic connection that connects the two from our V0 dominated system to our V1 dominated system. Okay, one thing that I wanted to add based on that. So then the key findings that we were able to show, this is first rigorous description of the spectral phenomenon. So it all opens avenues for multiscale spectral analysis. So we're able to show that for sufficiently small epsilon, the eigenvalue in the spectral gap correspond exactly to those of the scale potential V1. And the total number of positive eigenvalues of Laplacian minus W equals the sum of the positive eigenvalues of Laplacian minus V0 and the sum of positive eigenvalues of Laplacian minus V1. Okay, and we're able to do a rigorous, use a rigorous framework, combining dynamical system and spectral theory. Okay, so then one thing that I didn't want to introduce in the first slide, because I mean, it's not a lot, right? So basically the scaling that we chose, it matters, right? So if we chose epsilon, the epsilon squared that we scaled, this V1, is it actually matters. This is called a Fecal-Lieb-Rosenblum bound. So basically, if epsilon was not squared, if it was strictly less than 2, so we would have V1 dominate. So you only had contributions from V0. Because it's exactly 2, you get the critical case for the spectral additivity. And then if it's strictly greater than 2, then you get V0 dominates, right? So then you get the MW will be basically MV0. So the scaling of this epsilon parameter, it also counts. So this is one thing that I wanted to add there. So then the conclusion, so basically establishing spectral additivity for scale separated potentials. I have geometric frameworks that unify spectral and dynamical system perspective. And of course, there's future work. So I'm going to look at weakened regularity, so LP potentials basically. And we could also go to non-radial potentials and application to nonlinear Schrödinger NNS stability theory. So the idea that we want to look at this nonlinear Schrödinger equation with this nonlinearity, cubic nonlinearity. And then so the idea here is also has the same specificity that we want. So we're also going to look at this radial case, and then it has application in physics and of course it's other subjects. And there also is something about stability that we want to study. I mean, in the past, there's orbital stability have been done for epsilon equals 0. And then this operator that we're going to get is going to be called JL, is going to be Hamiltonian. And then the essential spectrum for this case is going to be on the imaginary axis. And the gap is going to be from on the imaginary axis from negative I to I. Okay, so the idea is to use this scale separation approach, but then to study the soliton and what happens as we add this perturbed potential with eigenvalues. Are there eigenvalues generated in the gap, basically, in the spectral gap? Okay, so then these are my acknowledgments. So I want to thank the NSF for their previous support. And then these are my other collaborators' support. And then I also want to, Jeremy, which his problem was stemmed from one of his PhD students, Dimitro. And basically there's this professor named Kenji Nakanishi that kind of stemmed this original problem, where we kind of have some wonderful analysis to do and to talk about. Okay, so then I want to thank you. And if you want to scan this barcode here, I mean, scan this, scan what you see here, it'll take you to our preprint of our manuscript there. Okay, this is all I got. All right, so I hope you guys didn't fall asleep. I hope I didn't bore you guys. But thank you.
Great, thank you, Emmanuel. It's really interesting. Seems like it's a potentially really powerful method. So I guess first let's just thank Emmanuel. So I'll click the clapping emoji a couple times and clap also, and then we have some time for questions if anybody has any that they'd like to ask. Yeah, go ahead, Nick.
Yeah, hi. Thanks for the talk, Emmanuel. Nice to hear, and something I didn't know anything about before. I wanted to ask, going back to your motivation of showing the different scales in atmospheric flows or just fluid flows, what would the additivity of the eigenvalues mean for the properties of a flow like this? You mentioned the either having emergence or having additivity. So how would that reflect on the properties of a fluid flow, for example?
Yeah, that's a very good question. So then the idea here is if you had a solution like a steady state, like let's say you had some solution to the coupled system that you kind of have, this will tell me what would happen as I evolve this system, as I take this steady state and I evolve it in time, and I add this whatever that you're adding, a potential that's perturbed. It could basically tell me that if this is going to be dispersive or if it's going to remain stable, right, as time goes by. And that's the general idea. I mean, so it's either you create scattering behavior, or you get something that remains stable as time goes by. And that's the general idea of what this work is going to show you for this particular problem. I mean, I have not done it in a real application. So, but you know, this in this setting that you mentioned, but I'm thinking that there could be some applications, right? But I have not applied it in that particular setting.
Yeah. I mean, something this reminds me of is that in Koopman operator theory, if you change a parameter of the system and approach a tipping point, that then the spectral gap vanishes. And that if you add more heterogeneity in your system, the spectral gap can already become a lot smaller, meaning that you have intermediate tipping. So I'm not sure if it's related, but it kind of reminded me of that.
I mean, that's a very good point. And yeah, so there could be some relationship, but I would have to read more about it. Right? That's a very good point that you just made. Thank you for this wonderful question.
Thanks. Very interesting talk.
Yeah, thank you.
Go ahead, Justin.
So to pose it differently, or to phrase it in a way that makes sense to me, are you saying the finiteness tells us that there's existence of asymptotic stability? That's my understanding of it.
Well, I understand what you're saying. So so when you say finiteness, you mean the finiteness of the like bound states, like eigenvalues?
The finite number of eigenvalues is you're able to count it, and it doesn't. On the other side of the gap, not the essential spectrum, but the discrete side, I suppose. Lack of my better understanding. Instead of it being an infinite number of eigenvalues, it's finite, which means there exists asymptotic stability at some point.
Well, okay. So
Clarify it for me.
No problem. That's a very good point you made. So the idea here is under the assumption that I presented for these potentials, right? So you have eigenvalues that are being contributed by V0 and V1. So then what this tells me here is Laplacian minus V0, right, has an unstable eigenvalue, for example. And then so the goal of what we've been doing is let's say we add another potential and we scaled it correctly, epsilon squared. So what you get is you get some additional eigenvalues that appeared in something called spectral gap, and then that adds to this instability that I'm looking at, right? So then I'm sorry. So then the idea here is like yes. So basically, if under these assumptions you only have finite amount of bound states, finiteness, and then now by adding this scale potential, you're able to see that there is contribution that's being done. So in the physical sense, what could that bring? I mean, there's different ways you could approach this, but I mean, it would require like more explanations and like understanding like different type of solutions that I did not talk about in this particular talk. I don't know if that answer made sense.
No, sure, it's fine. I appreciate it.
Okay.
Okay. Any other questions? I have one that's probably wouldn't have I'm not even sure if it's a good question. But the form of
There
that,
are no bad questions.
yeah, the form of that operator, and then the way that you sort of separate the scales reminds me of something I haven't looked at in a long time, which is two-scale homogenization, where you're basically, like, you often have like a Laplacian and some gradient, and it's a physical governing equation, and it could be electric fields or continuum mechanics equations, things like this. And then you basically separate the scales by making this epsilon argument, right? Dividing by epsilon and taking limits. I think there's any connection to that, like that?
Well, I'm not familiar with the two-scale homogenation technique, so
Right.
I'd say the connection would be the goal, right? So, I mean, I have a specific goal in mind, so I would have to look at what goal that, I mean, what is the end goal of applying this technique that you're talking about?
Usually it's to find some effective parameter so that you have like a simplified equation. Like if you had a composite of two materials that one was, one conductivity and one was another conductivity, what's like the effective conductivity of that whole composite material? And you can play some of these games to try to get at that. I know spectral theory comes into it,
Right.
but I've never, so anyway, at least connection, which is why I said it's probably not a great question.
Well, I mean, so I would have to look. I have not looked into that, so that would be something interesting to look into, right?
Sure, yeah. Cool. Okay. Any other questions for Emmanuel? Okay. If not, let's thank Emmanuel again, and see y'all next time.